Hello class, General Chemistry 2. We're going to be doing lectures online as I've already told you. I know this is just fantastic. You love me lecturing, and on video is even better. To limit your pain, I guess, I'll probably lecture for 14 or 15 minutes and then we'll take a break. You'll have to watch the next video. I'm going to set my timer here and we're going to go on to chapter 15. So chapter 15 is chemical equilibrium. Chemical equilibrium is the point at which the concentration of all species in a chemical reaction are constant. Is the point at which the concentrations of all chemical species is constant. Okay? Now we're going to see that this is actually a dynamic equilibrium, right? But the chemical concentrations will not change. So let's take a look at an example. Consider dinitrogen tetraoxide. Fantastic. The chalk, just wonderful. Gas goes reversibly to 2NO2 gas. Okay? No two-way arrow indicating reversibility, all right? So a reaction can go this way and a reaction can go that way. It's reversible. So let's take a look at the forward reaction alone. I'll use a one-way arrow only. Right? So forward reaction, again, no one-way arrow, right? And then let's look at the reverse reaction. Just simply reverse the equation around. Okay? So again, reversible reaction, forward reaction only, reverse reaction, right? So let's write out the rate expressions for both of these. And this is going to be a pain in the ass because I have a limited board to work with, so there's going to be lots of erasing and whatnot. All right, again, we're going to write the rate equation for each of these. So rate for the forward reaction, we're simply going to have our rate is going to equal Kf, the rate constant, little f for forward, times the concentration, right, of our reactant, raised to its stoichiometric coefficient, right? That's for the forward reaction. We do for the reverse. We have Kr is the rate constant for the reverse, little r. Again, times the concentration of our reactant, squared, because our stoichiometric coefficient is 2, right? So this is what we have. Rate forward, rate reverse, okay? Now at equilibrium, these two rates are going to equal one another. Or if I stick these expressions in there, like that. Let me quick erase this. Okay, this is what happens at equilibrium. The forward rate equals the reverse rate. So the chemical species are a constant concentration. The rates equal one another. Again, this is a dynamic equilibrium. You constantly have chemicals going from reactants to products and products to reactants. Let's quick solve this. Let's separate these out, okay? So I'm going to put the Kf and Kr on this side, and I'm going to put the chemical species on that side. So divide through by Kr. And I'm going to divide through by the concentration of N2O4. And this is what we get. Rate constant forward reaction divided by rate constant reverse reaction equals the concentration of NO2 squared divided by the concentration of N2O4. So again, this is at equilibrium. So what we're going to do is we're going to take this Kf times Kr, and we're going to let that equal a capital K, which will be called the equilibrium constant. All right, so again, forward rate constant divided by reverse rate constant equals K, sorry, not the rate constant, the equilibrium. The equilibrium constant. Sorry about that. The equilibrium constant, right? K, capital K, that's what that's going to be. Let's examine equilibrium though a little bit more closely, okay? I want to take a look at figure 15.2 on page 613, okay? I'm going to quick draw them on the board. But we want to just talk about equilibrium a little bit more. We're going to come back to this equilibrium constant K. It's going to be very important, okay? The next several chapters are going to be dealing with that. So again, figure 15.2, page 613. All right. So we're going to have here, we're going to have concentrations. Okay. Concentrations of our chemical species, specifically our N2O4 and our NO2. And then here, we're going to have over time. Okay, increasing that way. Now, let's say we start off with N2O2 and no NO2. What's going to happen, again, let me write a reaction up here, so you can see what we're talking about. Again, reversible. Right, there's our reaction, right? So we start off with N2O4 only. We're going to be up here. Down here, we'll start off, we're going to have no NO2. As soon as our reaction starts, we start going from N2O4 to NO2. As soon as our reaction starts, we start getting NO2. Here, down here, we're at equilibrium. Okay, at equilibrium, again, notice the concentrations of these are not changing, right? They're constant. That's the main point. If we take a look at the rate, now again, I told you this is a dynamic equilibrium. So these concentrations are the same, but I told you the forward rate equals the reverse rate. So let's graph the rate here. Again, this is in figure 15.2, page 163. Let's take a look at this. Again, I have rate on the y-axis. I'll put my time again on the y-axis. Having problems with my chalk as usual. Right? So again, at equilibrium, the two rates have to equal one another, right? So we're starting off with N2O4 only. So the rate at the beginning for N2O4, here we're going to have rate is high. The rate at the beginning for NO2 is actually 0. We don't have any. We're starting out. But what happens? The rate decreases as we're going from N2O4 to NO2. This rate increases until, again, at equilibrium, they're equal to one another. The forward rate equals the reverse rate. Sorry, got some crap chalk. So again, this is the main point. Again, at equilibrium, the concentrations are constant, okay? At equilibrium, the forward rate equals the reverse rate. I'd ask if there's any questions, but there's no one here. If you do have a question, by the way, email me, and I will send out the response to everyone. And by the way, I find it exceedingly weird to lecture to a video camera. Actually, exceedingly weird. But anyway, we'll go on. Let's talk more about the equilibrium constant. Let me check my time here. Actually, I'm going to end right there, and we will come back.